Thank you everybody for coming to this week's presentation. I'm going to talk about the stochastic gradient method, mostly from first order, not the second order. But this will be the outline. So first I will start with some statement of the problem of where we do need some form of a stochastic gradient, some setting, some parameters. There will be lots of notations here. Some fundamentals, lemmas, and assumptions that you may need to prove some of those things, and you will see that repeatedly you're using those assumptions, those lemmas in the same way. Some convergence results, and then some further discussion as time goes. So let's see if we can cover everything. Start with some definition, some input space cal x, output space y, and then there is some unknown mapping O, a mapping between x and y, and the whole idea here is somehow to find this mapping. We can have a data set of n training examples. Those training examples, we can assume that they are coming from some unknown, usually distribution, that unknown distribution, joint distribution actually between x and y. Or we can assume that there are some deterministic samples not coming from some joint distribution. That's it. So this is the samples, and just a notation here. This is a set from 1 to n. So with this notation here, the true output we know that is O of x, and our prediction is h of x, which is parameterized by some w, and assume that w comes from some space of this w. Everything clear? So this is a parametric function of h. So instead of writing h, you can see that we will write w. So they're the same. You can write w or h. They're the same. And we will iterate over w. And once we say that we converge, it means that we find the optimal h. Okay. We have a loss function f from the cross space of x, y, and r that measures how good we are on a particular sample x and O of x pair. And then we have a mapping on f, just another notation, fi of w is f of xi, O of xi, this sample, and your prediction. So this is somehow a loss function on that very specific sample. And that loss function is a function of your prediction function. And then we have an objective function f, which says which is a mapping between this fi, the error on individual samples, and the whole error that you want to have. And essentially, it says that how good your approximation scheme is. Some examples: expected risk could be the expectation over product space of x and y of fw. Now here you are assuming that the samples are coming with some probability measure defined on x and y, and this is the error that you do have on particular sample. So there is some x here underlying, of course, and then this is the average of the error, so the basis. Or you can assume that you're talking about the empirical risk, which is if you have n samples, and then this is the average of the error over those n samples. Okay. And then we know that if those n samples are IID and under some other assumptions, then this guy with central limit theorem can converge to this guy. And then we have optimal hypothesis, which is defined as this. So this belongs to arginf of you are optimizing over w of f. Okay, so everything's clear here. Very simple things. We will see this a lot here, but okay. So the usual gradient method, which is also called batch gradient, is as follows. So you will iterate based on this. So you will go for wk plus 1 at iteration k plus 1 is equal to the previous one minus some step size, which should be positive, minus some step size, the gradient of f evaluated at that function. And again, remember that this f is the whole error, so it's not an error on just one sample, it's the whole error, the whole function that you want to estimate. Okay. And then one specific example, in a batch gradient, you're assuming that if you are given a data set, then this is the actual gradient over the whole data set here. So that's the meaning of this. So actually here it is just nothing but the gradient of this guy. Okay? In the stochastic gradient, on the other hand, what you are assuming is that you will do the same iteration, but instead of updating based on this gradient, what you will update is update based on some g, which is another mapping, another function that takes as an input this wk. Wk was that function at the previous iteration, okay? And then you want to do this iteration with the hope that this iteration is somehow contracted mapping, and then you can converge, okay? And then this guy will be parameterized by some zeta, and then what is the meaning of this zeta? This zeta is nothing but just an index, and this index is, let's say that this is, the output of this eta k would be sample number 1 or sample number 10, some random index, and then g returns the gradient, some form of the gradient of the actual function at gradient of the actual function evaluated based on wk and for sample number 1. Okay, and then so the idea is that this guy should be somehow, doesn't have to be, but the main idea is that this guy is some sort of your estimation of the actual gradient. Due to many reasons, you may not have, or you don't want to have, the actual gradient. So then you can have an estimation of the gradient, a noisy estimation of the gradient, and this is the noisy estimation of the gradient that you can put on here. Okay. Just we will see this later on a lot. This table. In the batch gradient method, we have an expensive per iteration cost. Why? Because this is what you would do in every iteration, right? So in every iteration, what you do need to have is to be able to evaluate this guy, okay? If you assume that this wk or this evaluating of this gradient is cheap, then you have low complexity of finding this guy. But if you assume that n is large, then you need to have lots of these computations and then taking these expectations here, okay? So usually you have expensive per iteration costs that will usually linearly, at least linearly scale with n. But then the thing is that you need a few of these iterations usually. Well, the few means with respect to the stochastic gradient. Now in the stochastic gradient, what we will do is that, just to make it simple, you will see this later on, but just to make it simple, assume that this guy is just one random term out of this. Just one random fi here, or the gradient of fi at wk for some random I here. So just place that here. Then that's very cheap, definitely independent of n. Okay, in the general basic version of a stochastic gradient, it's independent of n. But on the other hand, you need many of those iterations, okay, to converge. We will see this table later on. Actually, how everything would behave as a function of n. And the main trade-off is the trade-off between these two. So, can you afford per iteration cost, or you can afford number of iterations? And based on which of them is better for you, then you can go for batch gradient or stochastic gradient, or something in between called mini batch gradient. Okay, so let's dig into that. Some motivations, of course, we would have some theoretical guarantees for that. For the batch gradient, again, what's batch gradient? You have the whole gradient for all those points. Okay, so for batch gradient, you can have this at iteration k, the function that you will evaluate minus the optimal function, the function that you can evaluate, or the loss that you can have if you have the best w. Once k goes to infinity, this would be in order of some rho to power k for some constant rho between 0 and 1. This is called linear convergence, okay? And then from that, what you can conclude is that if you want to have epsilon optimality, namely this guy is smaller than some epsilon, the total number of computation that you need to have is of this order. So you need to have this guy less than some epsilon, so then it would behave like the number of samples would be in order of log of 1. So this is n log 1 over epsilon. Okay? Am I clear here? Right? So you need to have this per iteration, and for every iteration you need to have n computations. So this is the total work that you need to have for epsilon optimality in batch gradient. In stochastic gradient, on the other hand,
what is epsilon?
Epsilon for epsilon optimality, if you want to have this term smaller than some epsilon. So you want to have closer between epsilon ball of the optimal solution.
W star is the optimum solution.
Sorry?
W star is
yes, W star is the optimal solution. And here underlying assumption is that this guy here is less than minus, is more than minus infinity. So there is some f inf, and then you are converging to that f inf. Okay? So the whole function over the region that the function is defined, so over the whole support, there is some minimum, and then you want to go to that minimum. So this is the underlying assumption. We will see that later on, actually. So now, actually, I'm just providing problem statements, motivation. Later on, we will see all the results, actually. For the stochastic gradient, on the other hand, first of all, you can't have this form of deterministic guarantee. What you can have is some form of stochastic guarantee. So you can say that there are many other forms, but this is a very simple form, and then you can see all the trade-off with this form of the guarantees. You will see later on some other form, so you can change that to some other form of guarantees. But here, with this form, you have the expectation of this guy would be smaller than this. So first of all, you will see that here you have a sublinear rate. So this is called linear rate, sublinear rate. But then, if you want to have this guy smaller than some epsilon, then you need to have 1 over epsilon total work. Why? Which is not being scaled with n, simply because at every iteration, everything is independent of the num n, actually. And what is n? N is the size of your data set, if you want to learn over that. Or the number of measurements that you have. And then everything is somehow comparison between this guy and this guy. So here, per iteration cost versus the number of iterations somehow, and the number of iterations with almost no per iteration cost. So this is the trade-off, which of them you favor in your situation, okay? Definitely you can compare that with very large n, and then you can see that this can beat this guy for large n. Okay, this is one thing that I mentioned. So we can have a very heavy computation with batch gradient, especially with n goes to infinity. And then you can have, if you have a heavy communication, we'll come back to that again. So if you have a heavy communication, we may not favor sending all those gradients. Just assume that we have a distributed computation or distributed processing where these guys will be computed at different sensors or at different points, and those nodes should communicate their signals, okay? And then there is some central entity, central controller that will run this guy, okay? So then you don't really want to afford these form of iteration simply because you don't want to have these many transmissions, okay? If you have a bandwidth limited distributed optimization form, and another motivation completely outside of this is something like security, where you don't want to send the actual information, the actual gradient, or even the actual data. What you can send is you can send a noisy version of that. And then you can have some sort of guarantee. Still, you can find the optimal solution. So everybody's like a win-win game. Okay, so that's enough, I guess, for that. So let's now be a little bit more concrete. The first thing is this. So a generic stochastic gradient algorithm, you will initialize W1, and for all iteration, you will do that. Very simple things. So you need to be able to have access to this function, which is a random realization of a random variable zeta k. Again, zeta k is just one index or a set of indices. Okay. Then you need to compute, or to be able to compute, a stochastic vector g. Again, for sake of simplicity, assume that this. Where is this? Here. Just to make everything simpler, assume that this g of wk characterized by zeta k is nothing but gradient of f zeta k at wk. That's it. So zeta k belongs to this set of n, meaning that 1 to n. Okay? So it's just one index, and then you will take that set. And if you assume that this is a noisy version of that, then you can add some z, some noise, or whatever. Okay? It doesn't have to be noise, so it doesn't have to be a noisy version. The thing is that you have just one sample and you want to iterate only based on one sample. So this is the most simplest scenario that you can assume. So that is your G here. So anyway, you need to be able to compute that. Once you generate this zeta, you need to be able to generate that. So given zeta and W, you need to have access to this line. And then you need to have a step size, alpha k greater than 0. We will talk about this step size later on a lot. And then once you have these three functions, then you can update your W as this. So very, very simple algorithm. Okay? WK plus 1 would be WK minus alpha k multiplied by this G function here. And then recall that f of I that I mentioned there is f evaluated at point I, which is xi and O of xi. And it's being characterized by W, y is by W. It means that you have this function h of xi at W. Okay? Some examples. This is just one example, but some other example of G function is like this. So this is the one that I wrote that. But then you can have a mini batch. So the average of this function over nk samples. So here in that scenario, instead of this zeta k being just one sample, you can have a set, a random set out of this set of 1 over n. 1 to n, and or you can have a re-scaled mini batch. I'm not covering this, but later on throughout this set of seminars, we will see this. So this is another way to improve the speed and lots of other things. But usually what you would do is that you will multiply by some positive matrix, positive definite matrices. It doesn't need to be PSD, just positive definite, I guess. But then you will multiply that just to re-scale this. And batch gradient is nothing but this nk equal to n. That's it. So for the whole samples, okay? Stop me whenever you have a question. So this is the whole problem statement. Throughout this presentation, we will talk about this general framework or this general algorithm. Okay? The first assumption 1, Licious continuous gradient. The objective function. I should say that all the results that we will see.
Sorry, you want to prove the convergence of the algorithm right now? Or?
Yes, we will see the proof. So here is we have something. We have some theorems. Just to let you know, we have some theorem here in this third section. We have some convergence result and some proofs. And for those proofs, we need to go back to those assumptions. But the thing is that for some sort of simple proofs, we need those assumptions. Just to have some simple proofs, we need to have these assumptions. If you remove this set of assumptions, you still may be able to say something in some very special scenarios, okay? But for this, I wanted to keep everything general, okay? And very easy to understand. Some general situation, what you can expect once you run stochastic gradient, okay? So the first one is Licious continuous gradient, which says that the objective function should be continuously differentiable with some bound on its gradient, which is essentially like this. So the gradient at any 2 points of W should be, again, what is W? W is this hypothesis over which you are optimizing, the hypothesis function, over which you are optimizing, which comes from some class W. So the thing is that this gradient is Licious continuous with Licious constant L. And a direct consequence of this guy here would be this inequality. We will use this inequality a lot later on. Is smaller than f of W2 plus the gradient plus term 2, right? Taylor expansion. Okay. Any question with this? Okay, simple assumption. Assumption 2. First, we should observe that WK plus 1, if we go back here, wk plus 1 is a function of this zeta k, right? And wk was a function of zeta k minus 1, okay? So first observe that wk plus 1 depends only on zeta k, and for sake of simplicity, again, doesn't need to be in the heart of all algorithm, but for sake of simplicity, assume that the realization, these random variables, zeta k over k, they are IID, for sake of simplicity of the analysis, okay? Now, what is this? This is expectation over the distribution of this zeta k, okay, of f of wk plus 1. So, this is very clear, okay? So now what is lemma 1? The lemma 1 is that under assumption 1, so if this function is has a Licious continuous differentiable, then under this assumption we can say that generic stochastic gradient algorithm would satisfy this inequality, which is pretty important. We'll use actually in almost all the proofs we use this inequality. Okay, and what is this inequality? This is just nothing but just using this inequality. Okay, so this is the proof. So in this inequality, we will just plug in wk plus 1 here, wk here, and that's it essentially. And then of course we need to take an expectation here. So just see what would happen. Here, plug in wk plus 1, wk, and then take expectation. Here, expectation over wk, you can take it out of that expectation. So that's the meaning here. So you would have this guy minus this, would be smaller than the whole thing here. Okay? That's it. Any questions so far? So these are nothing. These are some lemmas that we will use this inequality. We need this inequality for almost all convergence proofs. Okay, we will come back to these inequalities over and over and over. Okay, but some comments on this actually. So if we look at this inequality, what it essentially says, it says that taking an expectation over this zeta k, what you can do is that you can now take another expectation over all this zeta from 1 to k, just to have a total expectation, okay? Just to get rid of this cut here. Then you would have more or less the same inequality here. So what it essentially says, it says that this is the improvement that you can have, the average improvement that you can have over iteration k, right? So again, in iteration k, you will update and then find wk plus 1. So in iteration k, what you can have, this is the whole improvement that you can have. It says that you would have an expected decrease here, okay? Why it's expected decrease? Well, it would be decrease if the sign of this guy is equal to the sign of this guy, because we know that this is positive. But later on, we would have an assumption here that you will see. That this assumption makes sure that the sign of this guy is equal to the sign of this guy. So making the whole thing here is positive. And to make sure that at each iteration, we can have this term positive, so some decrease, okay, here. But then there is something that you may not be able to get rid of that. And this is something that we can call it noise. We will see that later on. What is essentially, it is something related to the variance of these stochastic gradients. Okay? So if you have a stochastic gradient whose variance estimation error is not vanishing with k, then, and assume that this alpha k is fixed, so constant the step size. We will see this later on, but just to make it clear why this term is important. Assume that this is a Licious constant, so positive. Assume that this guy is a constant, not vanishing. And assume that you have a constant variance for the noise of this stochastic gradient, I mean. If so, then this guy will not go away. So, and if there are some situation over which this guy goes away as time goes on, we will see this later on. If so, well, just to make it clear, it can go simply because this guy can go to 0, right? Because we have a gradient that can go to 0 as if you have a contraction mapping and everything like that. We'll see this later on. But this guy, at some point, this guy can vanish, but this guy will be here. So then you can imagine that this iteration cannot converge under this situation. This iteration cannot converge to 0. So you wouldn't have, you can converge to some uncertainty point, but you cannot converge to the actual solution, okay? Just to make it clear, well, for one specific example, if we assume that this g function is an unbiased estimate of the gradient, then we can just replace here, because this is an expectation, so here that would be the actual gradient, and then everything would be much simpler. We will use this inequality again a lot. So I did nothing but just replace this guy, this g function here, that's it. Okay, clear? Okay. Assumption 2. The first thing in assumption 2 is that the sequence of wk is contained in an open set over which f is bounded below by some scalar f in. So it's nothing but you are iterating and then finding some w. Just to make a little bit more restrictive comment on that, assume that the whole set of functions over which you are optimizing, the whole cal L, w, all the evaluation of the function over that is bounded below by some scalar f in. Okay? Just to say that you can converge to some point at some ultimately if you just run it over and over this cal f. Okay? So it's not that much restrictive to me at least. The second thing, now everything gets more interesting. The second assumption here is there exist two scalars, mu g and mu should be greater than 0. That for all k, for all the steps of this, for all iterations, these would be positive simply because we assume that this guy is positive. So it essentially says that on average sense, not on each iteration, but on average sense, we are moving on the same direction of this gradient. Okay, so this is the meaning of this. So in expectation, we have the same direction as the gradient. And if so, then we can make sure that this term here is positive. Okay, so this is just for that. The second term says that, so on average, we are moving toward the same direction, and on average, the norm of our movement, because our movement will not be determined based on the actual gradient, but based on this g function. Okay, and the norm of our movement is somehow comparable with the norm of the batch gradient, the actual norm of the actual gradients. Okay, so these are these two assumptions. Definitely, this guy should be smaller than infinity, of course, to have this guy some sense, of course, to make sure that this guy does make sense, of course. And then we have assumption C. So if we have these two assumptions, we can say that in every iteration we are not. So if I go back to these iterations, let me see. Yeah. So this is our iteration and this is the batch gradient iteration. What we can say is that we are moving on expected sense, not for every zeta k, but the expectation over zeta k, we are moving on the same direction here in expected sense again. And the norm of our movement is somehow comparable with the actual norm. Okay. So that is this. Essentially means that if we can't go that much wrong in every iteration.
But this, for this assumption, for example, A, can you say something prior to running the algorithm? Or?
Sorry?
Because this is something you have to say for each, like the iterations of the algorithms in the running. So I'm wondering, this assumption, can you check it before running the algorithm, or you can check it online?
You need to check it before running each iteration. The thing is that, for instance, if you have, I'm not sure if I do with automatic hold for mu equal to 1 and mu g equal to 1. So it's a property of your estimator, so as to say. Or for your case, if you're working with quantization algorithm, then this is a property of the quantization. So this is a property of this stochastic gradient axis that we have. So this is something that you can make sure by the design of your system, by the design of that g function or the class of g functions, you can make sure that these would hold. Okay. So if so, then probably you don't need to run to check it in every iteration or something like that. Okay. The last assumption here is that there exist some scalars m and mv, such that actually we don't need both of them. The only thing is that we just need this term here to be bounded, upper bounded by something. That the variance of our estimator is upper bounded by something. Okay? This upper bound can go to infinity because this is, you can see, the constant plus some mv multiplied by the norm of the actual gradient. And just assume some function like this. Assume that this is f. So m plus mv gradient of f. This can goes to infinity at these points, right? Once this guy goes to infinity, the whole thing can go to infinity. But what essentially this term is saying is that once we get closer and closer and closer to those stationary points or to the optimal solution, then this guy will vanish, and then we would have some variance bounds. So the variance will be smaller and smaller and smaller as we go more and more toward the stationary points. So this is the meaning of here, okay? And then we have a bounded variance close to the stationary point. So you can imagine that I mentioned that here we would converge to somehow to some region of the point close to the optimal solution, but we may not be able to find the optimal solution. And that is something that will be determined by this term. So in order to control that, either you should go for a set of functions with a smaller L, or you should play with this alpha, which is the step size, or you should work with your estimator. Make sure that the estimator error, the variance of your estimator, will go away as we get closer and closer to the optimal points. Some examples here. As I mentioned, for unbiased gradient estimator, you can simply double check that mu equal to mu g equal to 1 will satisfy this. So again, this is a property of your estimator, or your g function, whatever you want to call it. And then assumption 2b and 2c can imply this. Essentially, they say that, and what is this? This is exactly this term that, sorry for coming back again to this stuff, but this is exactly this term. So, so these two assumptions together will make sure that the whole thing here will be somehow upper bounded by some term mv plus mu g. And then you will see later on that if you want to be able to move toward the optimal solution, find the optimal solution, you should make these guys smaller and smaller and smaller. Okay? Okay. Everything clear so far? Sorry for lots of notation and assumption, we don't need that. So, lemma 2. Lemma 1, okay, smoothness of the functions, about the moments of the function. In lemma 2, we use now assumption 1 and assumption 2. Again, what was assumption 1? Assumption 1 was this guy, Liciousness of the gradient. And assumption 2 was this set of 3 assumptions. Given these 2 assumptions, then we can show that our generic stochastic gradient algorithm will satisfy this inequality. And we are going to use these 2 inequality, mostly this one, a lot. And that's just nothing. Just to prove that you can use lemma 1 and then these 2 equations. That's very simple proof actually. But then we're going to use that inequality a lot. Again, this is very much similar. So in order to be able to prove, I just use this one here. But then it has the same form as this, okay? Because it's just upper bounding. So what is this again? This is the improvement toward the optimal point. And then you can say that this improvement is somehow the trade-off between these 2 terms, the noise that you would have. So now you have a very clear notation here, to me at least. So you have improvement per term, and this improvement will go away as you get closer and closer to the optimal point, simply because this guy goes to 0. Okay? But then you can get stuck due to this term if this term is constant. So what you can do is that you can play with these 2, and then we will see later on how to play with these 2 to make this guy smaller and smaller and smaller. And if we can make sure that this guy goes to 0, then we can say that, okay, as we run this iteration, on average, we can find the optimal solution. Okay? And then convergence rate, of course, would be a function of these two. We can see why we can't start with alpha k very close to 0. Okay, the last assumption that we do need in some of those results, not all, is a strong convexity of the function. So the assumption is that the function f is strongly convex, meaning that there is a constant positive c such that this inequality holds. And then just to compare well, it's simple comparison, but just to compare the meaning of this strong convexity to ellipticness of the gradient, just compare this one with this, which was assumption number 1. So here we have an lower bound, and here we have an upper bound on W1. And then playing with these two, it gives us the convergence rate that we need. One very important inequality that we're gonna need is, starting from this, we can easily show that we do have this inequality here. Very, very famous inequality. How we can show that? That's very simple. Actually, this is a proof, but that's very simple. Just define this guy here, Q of W1, and then you can see that this is nothing but a quadratic function, so you can find the optimal solution for that. Take a derivative, make it equal to 0, and then find W1. And then replace that optimal point here. That's it. And if you do that, then you will end up to this inequality. It's a very simple inequality to find, but that's a very important inequality. Essentially, it says that whatever you do, the deviation from the optimal point, f star is f at w star. Okay, so this difference is somehow bounded, is upper bounded by 1 over 2c of this guy. We will see that later on, how we can use this now. Okay, any questions so far? Now we can run to the convergence results. So, the first convergence result is for a strong convex objective, assumption 3, and fixed step size. Okay, so just to recall, in the same situation, a strong convex objective and fixed step size, with batch gradient, we can have linear convergence rate. So this guy here can be upper bounded by O of rho to power some k. Okay. Here, we will see that's not possible here, so we would have a sublinear convergence rate here. So it says that for all k, under assumption 1 to 3, and assuming that f inf is f star, f at w star, and alpha k equal to alpha.
Sorry, what was f-inf?
F-inf was this assumption here, the first assumption, assumption 2, I guess. Let me see. The first one here. So this f over the whole sequence of wk, all the evaluation is somehow lower bounded by some f-inf. So this is the minimum things that, so loosely speaking, this is the minimum thing that you want to go over. And then here, the assumption is that this guy is f star that you like to reach, something like that. Okay. This guy, and if we have alpha k equal to alpha satisfying this, later on we will see why we do need that. Simply, it's very simple because we need to have. Yes, we need to have contraction here, and in order to be able to have a contraction here, then we need to have this guy here. But if we do satisfy this, okay, then the expected optimality gap, this guy, note that this is not expectation with respect to zeta k. This is the total expectation, okay, with respect to zeta way as k increases. And then you have this term as k goes to infinity, you have something like that. So as we expected, we have some improvement, and then we can convert to some region of uncertainty, which is somehow denoted by alpha Lm divided by 2c mean. Okay. How to prove that? Not that much hard actually. So now you should remember what is 7, b, 9, and 10. Probably nobody remembers. But there are just nothing. So this is 7b, then replace that, which would be 9, and then replace that, which would be 10. So we start with let me see, 7b. We start with this, okay? Then use this one, 9. As I mentioned, this is very important. Okay? And then finally we use this equation for alpha. That's it. So if we use that, then we can show that this guy is smaller than this. Okay? And then now what we need is to subtract f star from both sides, take the total expectation, and just rearrange everything, and then you can end up with this. If you like, we can do the homework and then try to evaluate it, but that's very simple. Actually, this is the whole thing that you need to know. And then finally, we will end up with something like this. But this is not a contraction so far, right? So just to make it a contraction, inequality meaning that something is smaller than some row multiplied by the same thing, and this row should be smaller than 1. So then you have a contraction. So then as you iterate, you get closer and closer and closer to the solution. Okay. Just to make it contraction inequality, that's it. What you should do is that from both sides you should add minus this term. And if you add minus this term, then you can see easily that this would hold. So add minus this term and then rearrange, and then you can find this. So then you have this term is smaller than this term multiplied by the same term. Okay. Now this one, just to make sure that this is contraction inequality, that's why you need to have this. So if you have that, then you can show that this guy here, the whole thing here, actually this guy here would be between 0 and 1, so the whole thing here would be 0 and 1, between 0 and 1. And that's it, essentially that's the whole proof. So then you can run it for, this is for wk plus 1, run it for w1, w2, w3, up to wk, and then you will end up to some term like this. And here, this is just nothing but this guy, move it to the other side of this inequality. That's it. Okay? Everything clear here? Sure. 2 questions.
Go ahead. Yeah.
So why do you need to assume that f inf is equal to f prime? Because you mentioned that the set is open, so it doesn't mean that this f inf you can convert to that point.
Yes.
So why do you need to assume that f inf is equal to your optimal point?
Just because here we want to have f star and then say that this is f inf. Otherwise, just replace that with f inf. That's it.
Okay.
No, we don't need that so much. Simply because it's a little bit cooler to have f star here. That's it. The only thing, I guess that's the only reason.
Okay.
Yeah. But otherwise, the only thing that you can say is that it's f at the star, at w infinity. That's it. Or wk infinity. That's the only thing that you need to have.
Yeah, okay. So I found it strange that now actually we have f star inside the expectation. So is it assumed, because before you had like expectation
You
of
can
f
take
k?
it out.
Yeah, you can take it out.
Yes.
So we're not assuming, there's no
Yes.
assumption that
No.
f star is moving.
Yes,
No.
exactly. No, you can take it out.
Yeah, just for the notation.
Yes,
Yeah.
for notation, exactly. Yeah, okay. It's just it doesn't important because as we mentioned, we have it.
It's fixed.
Exactly, deterministic definition of f.
Yeah.
Exactly. So you can take it out.
But what's the trade-off between doing, if you look at the earlier step, like this convergence and using the batch?
We will go to that.
The
The difference is that here we are not converging to the optimal solution.
But you can also imagine, for example, for the batch, that you converge to the same accuracy, same epsilon. And if you compare the iterations to this algorithm and
That's a good point. The thing is that we should make sure that this term will not determine the whole that epsilon. So what he's saying is that just put everything as epsilon and then see how many iterations you do need for batch optimization, for the actual gradient descent, and how many iterations you do need here, right? But if that epsilon, the whole thing, that epsilon is determined based on this sum, right? If this term is negligible in that epsilon, then I would say that you do have the same convergence rate. But my feeling is that this term will be dominating this term. For extremely small epsilon, I mean. Because this time you can imagine that this term will go to 0 very, very fast, as opposed to this term. So if the epsilon is so large, nobody cares, of course, but if the epsilon is so small, then you have some meaning of convergence to epsilon optimality, then this term goes away, and then you have just this term. That's it. So I guess that this is the main. And if you want to make it closer and closer to 0, then you will see sublinear convergence.
This like L, M, C, and mu, those are constant depending on the function itself.
Yes,
actually.
exactly.
So this is not the design parameter.
Exactly. Well, this is a little bit design parameter, and this is design parameter as well, because this M is your estimator. So you can assume that you have your estimator function, so you can design that. And alpha is your step size, so you can play with alpha as well.
Yeah, exactly.
But then that's the problem. If you play with alpha, then actually let's go to the slide, because I have some comments on how you can make it closer to 0, and then what you will lose if you make it closer to 0. That's it. So some additional notes. Again, if you assume that this g function is an unbiased estimate of the actual gradient, then mu is 1. Okay. Now, if we assume that mg is 1, then we can recover the classical requirements on alpha for steepest descent, which is alpha should be between 0 and 1 over L. So some minor comments. Fast convergence to a neighborhood of the optimal value, because now here we have, here we have this convergence rate. So linear convergence rate in that sense to a neighborhood of the optimal value, but then we have a noise in the gradient that prevents us for further progress. This is the optimality gap. How we can reduce that? Just by reducing alpha. CMU, this is something that we can control. We have a perfect control on these two. For sake of simplicity, I think that this, now we have a given estimator, or given stochastic gradient. Then we don't have even control on that. The only parameter here we do have control is alpha, step size. Okay, so this is the optimality gap, and now contraction constant after k iteration is like this. Okay, so what would happen if? So the thing is that we are not converging to 0, we are converging to this. But what we can do is that we can make it smaller and smaller. Just assume that we divide it by 2. Okay, so now we are more closer to the optimal solution, right? Now the problem is that if you make it divided by 2, then you can use Taylor expansion of this guy, and then see that you need to have something like around twice number of iterations. So k should be doubled in order to have this same constant for that contraction, right? So what it says that if you make it half, just to make sure that you are closer to the optimal solution, you need to have twice number of iterations. And that's why that you can converge to the optimal solution, but at a sublinear rate now. And that's very simple actually to show that. But now we can have a simple modification around a stochastic gradient with a fixed step size. See the convergence, so that would behave something like that. So assume that this is number of iterations, and this is regarding this comment here. So the expectation of f of w. Okay, we know that it should converge to some. Okay. So how this convergence behave? This says that we will converge to some value here, which is alpha Lm divided by 2c mu. Okay, so if you start from W1 from here, then you will converge at some rate to this. What you can do is that after some point you see that you are converging, so let's say that this point you are converging. So what you can do is that you can make this alpha to half. So alpha 2 equal to alpha 1 divided by 2, but let's not call it alpha 2, let's call it alpha R2, R1, and R is this point. So this is R1 or R2, this is R1, and this is alpha at this point is smaller than half of the alpha at this point. So what does it mean? It means that now you can have another progress and then go closer and closer to the optimal solution, right? So you can do that once you get closer here. Then what you can do is that make alpha R3 alpha R2 divided by 2, right? So just assume that this is R3, then you can converge. Okay, you can see that. Now the thing is that I didn't depict the right curve. The right curve shouldn't be like this actually. So the right curve should be that this distance here is twice as this distance here, because due to this this iteration. So the amount of, let's say, the number of iteration that you need to converge is capital K. Capital K here, whatever it is, here it is twice of that. Simply because you have a worse contraction constant here. So you need to have something like twice number of iterations. Okay, so now you can count the whole number of iterations, which would be summation of 2 to the power R1, 2 to the power R2, 2 to the power 2R2, 2 to the power 4R3, and so on. And then you can see that now the convergence rate, now how many iterations you do need to have a convergence, that would be sublinear convergence rate, O of 1 over K you can converge now. So is it easy? It's a very simple modification here that we can have. So this is the behavior of expectation of this F function, and you can make sure, but then there is no suboptimality gap, and that's it. And then you can show that the effective convergence rate is O of 1 over K. Any question? Okay, good. So, the second result. Now go for a strong convex function. So that was for a strong convex function and fixed step size, and that's why we were converging to something like this. Now,
So if I have understood, I'm understanding very less today. I'm very tired.
sorry.
So this basically tells you that why you take fast decay and then you take very long
Yes,
time, right?
exactly. So you will converge to somewhere closest to the optimal point. Actually, the convergence is like exponential, which is called linear rate in the optimization.
In the very beginning, typically it shows this kind
Yes.
of behavior and then it takes long.
Exactly, and once it goes to that saturation point, what you can do is that now you will not get that much better. That's the problem. So after this point, your improvement would be somehow bounded by this, because at the end of the day, you know that you will converge to some point like this. So what you can do is that you can just make this alpha half. Then you can have a big jump here. And then you will run, you can have a big jump, and then you can have a big jump. So at the end of the day, the figure behaves something like this. And then at the end, you can converge to this F star. But the number of iterations that you need to have would scale as order of 1 over K.
So I have another question. So this kind of analysis, let's say you have n set, right? Let's say I have, hypothetically, I have a n set training data, but I have given you n by 2 training data in the beginning. And then after some time I am giving you another n by 2. So how the convergence will change?
The thing is that how you want to run this iteration, because if you assume that you have n data point here, the convergence rate is based on the assumption.
So I have given you n by 2 in
and
the
then you
beginning.
want to find the gradient.
Let's say that it goes somewhere,
Okay.
and then you cannot use that n by 2 anymore. You lost that, and I am giving you another n by 2
Okay.
data points.
Okay.
So I have a set, so I give you half set. You do whatever you like, and then half set is gone, and then whatever the result it came, you start from there,
Okay.
and then I give you another half set.
So this is mini batch, right?
Exactly.
Yeah.
This is what I wanted to say.
No, this is not mini batch. In mini batch, basically you have the n set, and then you are randomly sampling some of them.
have overlap.
Okay. And then doing the thing again, randomly sampling some of them. Again, you are doing it. It is not that. I have given you half set. You can do one single, one by one, complete stochastic gradient.
Okay. So that's
And
the
then
question.
then it goes somewhere,
Okay.
and then you are forgetting you do not have any more access to the data.
Okay.
You have a solution only,
Okay.
and then you are again. I am giving you another half set.
Okay.
You do whatever you like, and then you tell, is there any way that we can characterize what gap will be there in the performance if I give you the full n in the beginning?
There are two things. The first thing is that we should first of all try to formalize the distribution of the data sets, because if the second half, the distribution over the second half is completely different. Now I'm talking about some crazy example, but just assume that if it is completely different from the first half, then f star over the second half is completely different from the f star in the first half. So
But this convergence is some function of the n, right?
it is a function of n, of course. It is a function of n. That's true. But what I'm saying is that in that scenario, if the first half is some data sets.
I hope that you understood that what kind of scenarios I'm talking about.
Yes.
Any online scheme, I will have this kind of a situation.
Exactly. The thing is that if you go for some scenario like that you have a big data set, and then you randomly divide it to two subsets, set with half of n and the other set with half of n, and then you are assuming somehow the underlying assumption is that the distribution of the data here is almost identical to the distribution of the data here. If so, then you have a very good chance of being able to use the solution of the optimal solution over the first half as the initial point of the second half.
Yes.
But if it's the case that extremely rare case wouldn't happen in reality, but just hypothetically.
Assume. You take suitable assumptions.
Exactly. If hypothetically we assume that the distribution of the data in the first half is completely different from the second half, then the optimal solution in the first half is completely different from the second. So it just doesn't make sense to use it. Exactly.
We have to have some kind of correlation.
Exactly. Just assume that they are identical. The distribution wise they are identical. So it means that they have both the same f star. So it's very good to start with that. So then if you run this iteration over n, actually the thing is that this guy here somehow is independent of n, is a function of k, and k is the number of iterations. And the assumption is that at every iteration you're randomly picking one of those points with some distribution. Just as uniformly at random, you're picking something. And then this is the convergence rate that you can imagine. Okay? So that's why that everything convergence rate, these things are independent of n. They are just function of k. So if as a function of k, I converge to this point, what does this mean? It means that this is the optimal solution. If you assume that this is the optimal solution over the first data set, that would be exactly optimal solution for the second data set. And that would be exactly optimal solution for the whole data set.
Yeah, if it is everything is same.
If everything is same. If not the same, then what you can do is that you can start everything from this point.
Yeah, that is the standard way of doing it.
Exactly. And then the hope is that...
but can we characterize the this way? How far it will be from the previous solution?
That would be a bit hard, simply because at this bound, everything is based on comparison with f1, with f of w1. And f of w1 here, for f of w1, we put the worst case, okay? But here, the thing is that if we do this run, at some point, f of w1 would not be the worst case anymore, because w1 is, the assumption is that w1 is a good guess. The initial guess is a good guess. So then we should be able to somehow characterize, so I would say that the steps is as follows. So first, we should be able to characterize somehow how good is the initial guess, and from that point, then we can use this, because then instead of having k iteration, then we start from this point. But the thing is that we need to know how good is this, and if we know how good is this, we can then map everything how good is that to this iteration to say that we are starting from this in the second round. We are not starting from this, but we are starting from that, something like that. But we can talk about it offline, I guess. But that's a good point. Okay. There is something a little bit related called optimal transportation. Which says that if you optimize something, well, the whole theory is a little bit more general, but much more general than that. But in this context, if you optimize something, find some function over some data set with some distribution, okay? And then you want to apply your function on some other data set. Let's say that you have a training data set, a test data set, and you are training over the training data set, finding the best function, and then you are applying that on the test data set. But the thing is that what would happen if the distribution of the test data set is not identical to the distribution of the samples in training data set? If they are identical, then you say that, okay, this is the generalization error. If they are not identical, then there are some form of characterizing the worst case error that you can have. And this is called transportation, optimal transportation, which says that what is the optimal transportation? Characterize the worst case error that you can have. Once you have this some joint distribution that gives marginal distribution over the training and marginal distribution over the test, and then you are optimizing over that, and then trying to find this thing. So essentially, those body of work try to characterize the error that you can have if you learn on some distribution and then you apply that on something else, or the same distribution with some error or some noise in some dimensions. This is something that could be nice as well, but those words are not for like a stochastic optimization, these kind of things, completely different mass there. So that was theorem 1, and theorem 2, it says that now we have a diminishing step size. Now we have a little bit different step size here. Again, assumption 1 to 3 we need to have, so the smoothness of the function, strong convexity, and then those assumptions on the gradients or stochastic gradients. And then now assume that alpha k will satisfy this, so diminishing a step size. For some beta, which should be like this, we will talk about that later on. For some beta of this form and some gamma greater than 0, such that alpha 1 should be smaller than that. And what is that? This is exactly identical to this constraint here. Okay? Why? It says that this is the diminishing a step size, right? So alpha is decreasing and decreasing. And it says that the maximum of alpha should be somehow upper bounded by this guy. So this is the meaning of here. Then the expected optimality gap will satisfy this. Again, you can take f star out of this. Nothing will be changed. Where v is the max of these two terms. Okay? Nu is the max of these two terms. Well, some note. Asymptotically, using some inequality, you can show that this term actually will dominate this max, okay? But not for all k. Asymptotically, it will dominate. So asymptotically, you would have beta 2 Lm divided by this guy here, okay? How to prove that? Again, we should use lemma 2 and equation 9. And what was equation 9 again? I'm coming back to that because this is pretty important. Inequality here, again you should use that, and then almost the same steps as of proof of theorem 1, you will end up to something like this, where you can show that you have this. So that is very similar to the previous one, except instead of having alpha, now you have alpha k everywhere. Okay, and now from that point you can prove this by induction. Okay, and somewhere you need to have this inequality, which is pretty easy, right? But the main proof is by induction. You just end up with the almost same contraction form. It's not contraction anymore, but then you can prove by induction. Okay. Some comments on this. First of all, now we have a new parameter in the step size, which is beta should be greater than 1 over c mu. What is the problem with this form of requirements? First of all, well, the most important thing is that this is very, very sensitive now. Why? Because if you have an overestimation of this c, then you have an underestimation of beta, right? And what is the meaning of underestimation of the beta? If I come back to the step size, beta is in the denominator of alpha, right? So if you have an underestimation of this, it means that you have an underestimation. You're starting from very small value of this alpha. And if you start from very small value of alpha, then instead of being able to converge at this rate, you will converge at something like this rate. So that's very horrible, I would say. So that is the first problem that you can have. So very, very sensitive to this. And then I mentioned that the first term will determine asymptotic convergence. Okay, now what would happen if we go for, now let's compare the first table that we did have. This is not for diminishing step size, this is for constant step size, but you can have more or less same comparison with diminishing step size as well. So for constant step size, theorem 1, and now let's compare mini batch, sorry. Okay, this is wrong. It's not diminishing a step size here at all. Okay, so this is comparison between constant step size, a stochastic gradient, and mini batch stochastic gradient. Everything is constant step size here. For a mini batch, define this G as this, and if you want to run it per sample, then mini batch is just n of m. Simple stochastic gradient is n of m equal to 1. N of m is the number of samples you will put in the mini batch computation. Okay. For mini batch with a small constant alpha, you can have this. So this is, I did nothing but just using this inequality here, plugging everything here. Okay, so this is just 11 here. Okay, so with a small constant size alpha, then for mini batch you can have this. The thing is that you have one n over m here. Why? So just look at this, alpha Lm divided by 2c mu nm. And the original thing was alpha Lm divided by 2c mu. So there were no nm here. What is m? M essentially is the as k goes to infinity, this m is the variance of the noise that you can have on your estimator, on your stochastic gradient. And if you have nm samples, then the variance, and those samples are IID, then this guy would be, instead of m, it would be m divided by nm. That's it, right? So is it clear? So this is a reduction in the noise of the estimator of the gradient due to mini batch. And then the same thing here. Okay? And constant small step size alpha. Now with simple stochastic gradient, in order to make these two terms, the asymptotic error identical, to make this a fair comparison, now we just want to compare how fast mini batch can go to the optimal solution and how fast simple stochastic gradient can go to the optimal solution, the same solution, okay, with the same bound on the error. So we keep these two identical. In order to be able to do that, here in mini batch we played with m, the variance of the estimator. Here in simple stochastic gradient we play with alpha, make alpha equal to alpha divided by nm. Then these two will be identical, and then here now we have this. So now if you want to make a comparison here, it's very easy to see that this guy converges much faster than this guy, something like nm times faster than this guy converges. So much less number of iteration, but per iteration we need to have nm computations and then find this guy and then plug in that stochastic gradient iteration, right? So this is somehow table number 1, so as to say. Any question about that? Okay. So again, here we have cheap iteration, independent of n, but now we need to have many iterations. So beyond strongly convex functions, now for just convex objective functions, so some relaxing assumptions. Now some more notations. The first notation is this one, which is the set of all subgradients of convex function. Now we can be even more general. Instead of saying that we should go we should work with gradients of those convex functions, now we can even go for subgradients of those convex functions. F. So then this guy G, actually, given WK, then this G is a noisy, unbiased subgradient of this. Okay, for sake of simplicity, in the simplest scenario, I assume that this is an unbiased, noisy version of the actual gradient. Okay, and then define f best as the minimum of the function evaluated so far. Okay, and some more assumptions. Bounded norm 2 of this g function, which we had previously. What was that? Previously it was m plus mg, right? Or n or something like that. It was just to recall here. It was like this. So m plus mg something it was previously, and now assume that the whole thing is like g squared. And then now another pretty important assumption is that the initial guess from the optimal solution is a bounded deviation from the optimal solution. So what you ask Saikat would be that now we have a better guess, so we have a smaller r if we start from a better point. But then we should be able to characterize how good is this starting point. Okay. So now with this notation, under some mod condition and for now diminishing the step size with this property. So they are square summable but not summable. We will see why we do need that. Actually, it's very clear here. We have this convergence. So we have a convergence in expectation in the sense that the expectation of f best, what was f best? F best is this. So the best function evaluated in the previous k iterations minus f star, the optimal solution will be bounded above by this. So that's why that we need to have this assumption, a square summable but not summable. Because if you have a square summable, then this is bounded, so less than infinity and infinity, so this guy can go to 0. Okay? And for any arbitrary epsilon and delta, we can have convergence in probability, some stronger results here. So the probability that f best minus f star being greater than some epsilon would be less than some delta for any arbitrary epsilon and delta. How to prove these results? So first of all, the statement is clear. So let's see. So again, it's not for a strongly convex. Now we relax the strongly convex assumption, and then we relax even having the actual gradient. We just assume that this g function belongs to a set of unbiased subgradients of f. Okay. To prove that, we start. Actually, now we go for w. Start from w. Previously, what we had done was that we started from f function. Now we start from the w functions here. The actual w. So start from w, use the convexity of the function, which is this, to show this. This is very simple. Actually, you can show that. It's not that much hard to show that. That should be and here. So take expectation and recursively apply that. So you have this for k. Apply that for k minus 1, k minus 2, k minus 3. Actually for 1, 2, 3 up to k. And k plus 1. And then sum everything together. Okay? And sum up everything and then take another expectation. You will end up with something like this at the end of the day. Okay. And that's it essentially. Why? Because this is by the definition R2. And then what? Then this is what you're looking for, right? Why this is what you're looking for? One question if you're following.
In the first line, I didn't understand why f is next page. Yes. Why f star is greater than this one?
Because you're using a convexity of
Convexity of f.
No, but g is random. It is not the
Sorry, here there should be an expectation. I'm sorry. There should be an expectation here. And since now we are assuming that this expectation belongs to set of subgradients, then that is fine.
Yeah.
That's the notation, so thank you for that. Yeah, we definitely need to have an expectation.
Yeah, we need an expectation.
Yes. Expectation, and then actually this expectation should be even conditioned on WK. That's right. Yeah, this is pretty strong assumption. You can have that for sure. Okay. That's it, right? So just one question I asked. Why from this, why this is what you want? Just to make it even simpler, you have, at the end of the day, you have something like the summation of alpha k and you get 2 summation of alpha. So this is exactly this, right? So you should be able to take it out. How you can take it out? No idea? Food for thought. Think about that. It's not that hard actually, it's very simple. Okay. Then from this you can easily conclude that we have this inequality. Okay? That's very easy from that to show. R2 is actually this term. The last term is this one, so you just move everything here to that and then that's it. Some error. I'm not sure, I should double check, but I guess that this should be plus. I guess that it should be plus. I will double check, but I guess that should be plus G2, and then again here should be plus as well. But this is the main step of the proof that you should have. And then, so here we have the proof here. Actually, even we don't have this guy. Why we don't have this guy even? Simply because what is f-best? F-best is this. So what we can show, but the main thing is that how you can show that actually. So what you can say that this E of f, minimum of these functions is definitely smaller than this. This is how we can, so just replace that with the minimum of this function and then use inequality, that's it. So using the inequality that minimum of this function is smaller than these functions, then you can recover minimum, you can recover somehow f best. That's it. And then take it out. Okay, so from this you can conclude something like that. So the minimum of expectation of fk will converge. But how you can, but this is not f best so far. Why is not f best? Because f best expectation should be here, right? So then you can use Jensen inequality and concavity of the minimum function just to take it out, and that's it. So essentially what you can say is that expectation of f best, okay, which is by definition this, is smaller than this guy here. And this guy is converging, which means that this guy is smaller than something, then definitely this guy, the whole thing is smaller than something. And that will be the proof of here. Okay? And for the second one, now you need to use just Markov inequality to show that actually the probability of this guy is smaller than the expectation of this guy divided by some epsilon. And you have a convergence result for this guy here, right? Using this inequality. And that's it. So essentially you can now show that the convergence is probable. And this form of proof is pretty standard. Clear? Why I'm trying to say all the proofs simply because at some point you may need to use a stochastic gradient and you are using at some point some of these lemmas and assumptions. So that will be for some future reference. Okay? Then the last reason.
I think people has to work on actually.
Sorry?
People has to work on. Means
Yes,
your slides will help that.
Yes.
Sit down and read. But I just got one big tutorial, some 95 pages in archive.
90 pages? Is it? I guess that it's
The one
probably.
with-
Yeah.
Yeah.
This is that.
Yeah, exactly.
Yes. Yes. Actually, I use that for most of these results.
Yeah.
For most of these things.
But is that thing? But some of the things you got from somewhere else, or everything
Yes.
is that?
No, not everything from that. Some of these results are actually from this book. This is a very nice book as well. And some of the results are from this. But most of the results, to be honest, is from this. And it's very, very nice. I highly suggest it actually to read. Okay.
Because
So-
some point of time I used Robinson-Monroe algorithm for designing something.
Yes. That's the simplest stochastic gradient.
Yeah, that is the one of the first 1950s algorithm. Actually.
Exactly.
And a very
1950s.
successful one.
54, I guess.
Yeah, close to that. It's a very successful one.
Yes,
At
yes,
that
yes,
point of time, we that actually works for large covariance estimation. We did that.
Okay.
But
Yeah.
I didn't know this.
Okay.
Yeah,
These are a
Lots
little
of
bit
validation.
generalization of
Yeah.
these Robin-Morrow's algorithm, but
Yeah.
that was the starting point of all these stochastic gradients. Okay, so that was term. So now I'm moving a little bit now faster, so you won't see so much of proofs anymore. So for convex objective function, now a little bit different from the previous setup. So what we did have, we started from strongly convex for fixed constant step size and diminishing step size. Then we moved to convex, not anymore strongly convex, and constant step size. Actually, that wasn't a constant step size, but this is one form of guarantees that I mentioned. Now it gives another form of guarantees here that you can have. So these are a little bit different from the previous one, right? One thing, I'm not sure if this 1 over k should be here, or this summation should be here or outside of this f. Do you remember? I guess, I'm not sure, but I will double check. But it might be that this summation should be outside of this. I'm not sure about that actually. I will double check.
Right. Yeah.
Anyway, yes.
Yeah.
What it's saying is that the only thing again is the supremo of this should be R2. We had that previously. Previously we assumed that this guy is R2, but now nothing would be changed if you assume the supremo of this guy is R2. So the same thing here, and now we need to have LFMUS functions, IID stochastic gradient with variance bound sigma 2. Okay, is it clear? What's the assumption? So here the assumption is that at every iteration we have access to a stochastic gradient, but these axes are IID, and all those samples, they do have a variance bound of sigma 2, and sigma 2 may not be vanishing. Okay, and that's why that you can expect that the whole error may not vanish, may not. And then here now we have a constant step size, not like previously where we had diminishing step size. And step size are coming of these four. Then we can have these convergence, which essentially says that the first term will go away at some point. If you remember previously, this term was of order of something to power k, right? So we had a linear convergence here, but now we have a sublinear convergence in the first term, and then we have a second term, and then the second term will go away as well.
Just a question. Alpha k is constant?
No, it's not a constant, it's diminishing.
Okay.
There shouldn't be constant. Yeah, because I was just thinking that it's here, we have this guy here. No, it's not constant. And if it was constant, then we shouldn't definitely be able to converge the optimal solution for sure. No, this is not a constant. Actually, I added that this morning. Okay, so just remove this constant. So there should be a step size of this form, and then we will converge at this rate. But at the end of the day, you can see that this convergence rate is 1 over k again. Okay, so it's not linear. By linear, again, it means that it should be order of something to power k. And for proof, you can see this Bubek book chapter, and let me see. Improved game for mini batch of size n. Okay. So I was just saying that here it just means that what would happen if you improve the mini batch, if you go for mini batch. So instead of assuming that the mini batch size, the stochastic gradient is based on just one sample, so one IID stochastic gradient. If you assume that you have nm IID stochastic gradient per iteration, then you can reduce this variance to sigma 2 over nm, and then just plug in it here to see how much gain you will get. Okay? Very similar to the previous results. So something like linear gain, because now you can take it out exactly like how you had here. So you have something like linear gain m, and if you have nm IID samples, then you can have m divided by n, right? So exactly the same thing happens, same results here. Two last things. Don't worry about the statements of the problem. These are for non-convex objective functions. Okay. Now another class of functions. The thing is that for non-convex functions, I'm not aware, at least, of any results on the optimality gap of the actual function. But these classical results are about how gradient of the function, or the norm of the gradient of the functions behave if the function is non-convex. Okay. And then now we should have assumption 1 on Lipschitzness of the derivative, and assumption 2, which says that the class of those gradients, or stochastic gradients, and then it says that for all k, okay, we can have some result like that. Just focus on equation 19, it says that the average of the gradient over the first k gradients, capital K gradients, the average of the norm will be upper bounded by something. Okay? Why is this important? What does it say? Just to prove, the proof is not that much hard actually. It seems to be hard, but it's very simple actually. So this is the proof that you can have. You just need to use these steps to find this one, and from this one you can easily conclude this one, and then divide everything by k, and then you can conclude this one. So the proof is easy actually. But just some intuition about from this equation. What does it say? What is the meaning of this guy here? Actually, I wrote it here. But try to see what's the meaning of that. Okay, so what it says is that if k goes to infinity, then the average error is somehow upper bounded.
So sorry, capital K here is different than small k. So capital K,
Yes,
you're taking
a
a
small,
fixed. Yeah.
exactly. Capital K is the average of all the norms of the gradients evaluated over the first capital K iterations.
Yeah.
Okay, and a small k is per iteration, and this is index set of 1 to capital K. Okay, so what it says that the objective function, let's say the gradient of the objective function, the gradients favor spending increasingly more time around spaces where this gradient has relatively smaller and smaller and smaller values. Why it is? Because you can show that this is a constant term, right? Everything here is constant, and as k increases, then this term is going to be smaller and smaller and smaller, right? So what does it essentially say? It says that as k increases, that will be one interpretation, I would say. As k increases, the stochastic gradient spends more time, more and more and more time over the region over which the gradient. The thing is that you will converge to, you will favor spending more time, this stochastic gradient iterations. Favor spending more times around the regions over which we have smaller gradients. Okay? And then as you can see now, we have the same, more or less the same result here for this, to say that okay, now everything is bounded by alpha, you can make alpha smaller. Smaller convergence rate is still, we don't know what is the convergence rate here because we don't know if we can converge to any point or not. But the thing is that we know, at least experimentally, that this alpha will reduce the convergence rate.
Okay, so here you're converging to a region around the stationary
We are not saying that we are even converging.
You are going
exactly.
towards some point.
Towards some point, but the thing is that now we can bound the gradient at least. This is a very
Yeah.
simple bound, of course. But this simple bound says that it just doesn't matter if we do converge or not. But we spend more and more and more time over the region with the smaller gradients. Okay? And if you are happy with those regions of the smaller gradients, then this is what you can get from stochastic gradient. Okay?
Like as in, because, and smaller gradients usually means that you're closer to the some sort of
Yeah.
stationary point.
Yeah.
Or something.
Exactly.
Stationary point of first order,
Yeah.
which is
Exactly. And if you say
Yeah.
alpha is equal to almost 0, okay, with some smart way, by some smart way I mean something like that. So you don't say that this alpha is diminishing by saying that okay, if you converge, then make alpha smaller, 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 then I guess that you may be able to prove that you will converge to some point over which this gradient is 0. Okay, so you may be able to say that you will converge to some stationary point, but if it's global or not,
No.
this is something totally different, right?
Yeah.
And this is the last result, I guess, the last slide here, which says that, again, for non-convex, a little bit different result. Just look at this one. Which says that, more or less the same thing. The main difference is that here you had constant step size, and here you have diminishing step size. So all the result was for strongly convex, constant diminishing, for convex, constant diminishing, and now for non-convex, constant diminishing step size. So for diminishing step size, you can have something like this form. Think about the proof. That's very nice way to prove that. Very simple. You have everything here. Actually, that's very simple actually to prove. But think about the proof. That's nice. Just as a homework, I would say. And then what you can say out of this, what's that? This essentially says this state. A little bit stronger than this, but more or less the same thing, I would say. So this says that since this guy goes to 0, okay, what is that? This is somehow, you can show that this is more or less the expectation of the gradients with diminishing step size, okay? It would say that the expected gradient norm, the norm of the gradient, of course not the actual gradient, but the expected gradient norm can't stay bounded away from 0. At some point you will converge. So this is what this result would say. If you run this iteration over and over and over and over, as case goes to infinity, then you would converge at some point. Okay? But to have that, you need to have diminishing step size, of course. Why? Simply because if you have diminishing step size, you show that from here this is finite, and this guy here goes to infinity, so the whole thing goes to 0. But you need to have a diminishing step size, okay? That will ruin your convergence rate, of course. Alternatively, you could run the constant and then use those halving trick or something like that again to converge. That's it. So some further discussions. Just something.
So there is any proof that if you have a fixed step size, you will converge?
You cannot converge actually. This is this theory. So all this theory says that if you have a constant step size like this one, you would not converge. Well, actually, I just picked the not constant step size. Okay, so this is a constant step size, and it says that you would not be able to converge. You will converge to some region, and it makes sense. Why? Because you don't know the exact gradient. So after you get very close to the actual gradient, you don't know the gradient, but you have access to a stochastic gradient, some random unbiased estimation, right? But then the thing is that this estimator may give you the error of that estimator is not being reduced. This will not be reduced by the actual gradient. So the gradient is close to 0, but that one due to error gives you some crazy gradient.
So this is a standard intuitive result. It's called jittering. It's if you are in the optimum point and you are close to that, you don't know how fast you have to reach. So you start, because of your moment of inertia, you basically jitter continuously.
Exactly.
Yeah.
Exactly. This is exactly like that. So this is due to the noise. So what you can do is that either you should damp that noise, either by improving the estimator, which means that using mini batch, for instance, here you can use mini batch. Let me see. You can use it's smaller than something like that for some constant tau. So previously it was smaller than some m for sure, but now it's smaller than m tau to power k. So as we progress, then the variance will be smaller and smaller and smaller. So then you can imagine that we can converge now. The thing is that how to realize that, one way to realize that is to use mini batch of this form. So just increase the size of your mini batch. So as time goes on, just increase the size of the mini batch of this form, and then you can easily show that this form of sampling, increasing the size of the mini batch as time goes, it would exactly simulate this form of variance. The variance would be smaller and smaller and smaller as time goes, and then now we can have a convergence rate of this form, and that's quite great. Okay, with a constant step size iteration. That's the first thing. The second thing is let me see. Okay, the second thing is this is a little bit more closer to our background, communication signal processing background, where you're assuming that instead of having access to noisy version of that, what is the source of that noise? And the source of that noise could be either recording using ADC or just sending through some band limited communication, and then you don't want to send all the bits. So then this results in some error. So the actual gradient that you have is not the actual gradient, it's the actual gradient plus some noise, which could be quantization noise or whatever like that. And then the thing is that if you want to model this as a stochastic framework, then the thing is that you need to have those IID things and everything like that, then probably you need to go for some random quantization. Actually, we had a discussion over that. So what is a random quantization, for instance? It will get as an input this gradient and report some random vector. or some random set of bits, and then from that random set of bits, the receiver will get something. But this random set of bits, the sequence, so to say, this random sequence of bits has some property. And those property are the property that we saw in assumption 2. Okay? The other thing is distributed system. I talk about that a lot. So we have a stochastic gradient updates, W, with a high frequency. And what would happen if you have some communication overhead? So this is something that we wouldn't have if you have parallel processing and all the processors are in the same data, in the same center, but what would happen if you assume that you have a set of sensors and they are physically located far from each other, and then now you need to pay some communication, real communication overhead. It doesn't need to be actually communication as long as it's some form of cost, and then you can model that cost, that's enough. So in that sense, you may have higher per iteration cost. And if you have higher per iteration cost, you go for more number of iterations that you would favor, but less per iteration cost, of course. Then the good thing, the interesting thing would be how to really model that. Okay, so something so as to say, going beyond characterizing everything like that as a function of k. So everything here that you saw is a function of k, k, k. I picked some of them that has no k here. So some k here, the number of iterations. So going beyond that, the number of iterations, so as to say, the actual cost of running this optimization, which could be either translated in the form of time or the number of bits that you need or something like that. So not just the number of computations. And then finally, I'm not going through that. And I just saw a very nice paper that finds some correlation, some relation between Markov chains and with the stationary distribution P and some stochastic gradient with constant step size. Just to make it clear why this could be a Markov chain, because if we go for this, lots of things to go back, but okay, here it is. So if we go for that, then everything as a function of this zeta could be a Markov chain. So if you see the evolution of everything as a function of zeta, then that could be a very nice Markov chain. And then you can now go for Markov chain, and then it's like you're running a Markov chain, sampling from Markov chain, and then finding the whole distribution over that. Then you can map this problem, solving this stochastic gradient, to finding the stationary distribution of the corresponding Markov chain. That was a very nice paper. And that's it. And these are two references. The first one is highly suggested to read, and of course the second one is much longer than the first one. By the way, this is 90 pages. So this is long enough. Yeah. Any questions? I guess took a lot of time. 2 hours?
No.
Okay.
I think a little bit less.
A little.
You can
2 hours. 2 hours. 5 minutes less than 2 hours.
So you finish the 5 minutes.
Exactly.
By the way, Hussein, why were the results on non-convex objective functions published? On the first or the second?
The first one. The first one is a very nice review, and it's published. I'm not sure if it is now published or not. I guess it's
Second is
accepted.
not.
And then the same author, they did have a very nice workshop on the last ICML, exactly on the same topic, and they covered actually all of them.
Okay.
The same co-authors. So they had a series of lectures on these optimization methods, and by optimization method they are mostly talking about the stochastic gradient for larger scale optimization. And that was a very nice workshop as well. They had in the last ICML 2 years ago.
Yeah, maybe something like that, 2016 or 2015.
I guess 2016.
Are the videos on?
Sorry?
Are there videos online? The videos that you mentioned for the workshop?
No, I didn't say that there is a video. I'm not sure if there is a
You
video.
can definitely find them on YouTube, of course.
Okay.
Yeah, if you search on YouTube
Probably,
the title of
yes.
the talk, then
Hopefully.
definitely you'll find them.
I
Yeah.
didn't really Google that, but
Okay.
you will enjoy reading the paper.
Okay,
I'm not
so
sure
the
if you
paper
need
is quite-
anything more than the paper.
Yeah, the survey is very nice. I think it's a good idea if we
Yes.
try to cover like parts of it later.
And I mentioned that this is not the best result that you can have or the strongest result that you can have, because some of those results are well, if you want to have some even stronger result in form of convergence, almost short convergence, for instance, then in most cases you need to work with martingales and these kind of things will mess everything.
Yeah.
So they went for somehow the smartest solution, go for simpler scenarios, and just try to illustrate the main trade-offs that you would see. But then there are tons of references in that paper as well, something
Exactly.
like 160,
Yeah.
170, something like that.
Exactly.
You can have your whole life just reading those papers.
Yeah, exactly. Exactly. Yeah, and that will increase like by the time we meet up next week.
Yeah. Okay. Okay. Thank
Yeah.
you all.
Thank you. Yeah. Thank you.
Sure.